All right, so now I guess all the rest of the talks are going to be on a more detailed technical level. So the problem we're going to be dealing with is how we perform causal discovery, particularly with constraint-based methods that I'm going to be discussing when we have mixed types of data. So again, the causal discovery problem is we assume there is a causal graph, a causal model, and that generates our data. The data come from a set of causal relationships. Of course, we don't know the graph. What we have is the data, and we try to reconstruct the graph or all graphs that fit the data. And that's the problem of causal discovery. Now, the types of causal models that we're going to try to reconstruct could range from simple ones like Bayesian networks that don't admit cycles and do not admit latent confounding variables. But there are other also types of graphs like maximal ancestral graphs that are mixed graphs and admit latent variables. The theory is much more complicated and sometimes the algorithms too. For both of these causal models, there are three basic approaches. One is score-based, where we try to measure the goodness of fit of the causal model to our data and score a model regarding the fit. And then we search in the space of all possible graphs to find the one with the largest goodness of fit. The constraint-based approaches are a bit different. They don't score the whole network, but what they do is they query the data for independencies, and whenever they find an independence, they constrain the possibilities of the final graph. They say, for example, this cannot happen, this edge cannot be there specifically. And in the end, we're left with all the choices that are actually admissible, and we can find we may end up with a single graph or all graphs that fit the data. And of course, the hybrid approaches combine the two. Now, in today's talk, I'm going to be referring to the constraint-based approaches. And anybody who has started on the subject of causal discovery must have at least seen the prototypical algorithm in the field called the PC algorithm. The PC algorithm, I don't know if you know how it's got its name, from Peter Spirtis and Clark Glimmer, right? Clark Glimmer. So it's the initials of the first names. That's because the previous algorithm, they gave the initials of their last names. All right, so the algorithm essentially starts by restricting the conditioning set to 0 initially, so that it's going to condition on the empty set, and repeatedly does the following for every edge still in consideration in the graph. It conditions on some variables, a subset S, and by producing a p-value in the data. And if this is lower than a threshold, it deletes the edge, okay, from consideration. So eventually, and then it increases the allowable size of the conditioning set. And eventually, it's going to find the presence or absence of all edges in the graph. And then in the phase B, it's going to orient the edges. But what is important is that the only access to the data is through these p-values again. So the question is, how do we compute these p-values needed in the algorithm when we have mixed types of data? Okay. And actually, if we figure out this problem, we can run the same algorithm on all sorts of data without any other change in the main algorithm. All right, so for some types of data, for example, when you have all continuous data or all discrete data, it's well known that you can run some condition dependence tests for these homogeneous groups of data, like G-square or chi-square test here and the partial correlation test. But what about the general case where you have different types of data? What are these different types of data you may have? And actually, we encounter this in real applications, when we work with real data, you may have, of course, continuous values, continuous variables, or positive valued variables, or percentages, or what's called clustered data. These are all continuous, but there are, in statistics, specific ways to treat each one of these cases. And they should be treated differently, actually. For categorical data, you may have binary, nominal, which are extension of binary, or ordinal, like the satisfaction level in a video call for people who work in quality of experience. Or you can have count data. So there's prior work on working with mixed types of data as early as '95, where Heckermann gave a score-based method for variables, for data sets that have both discrete and continuous. Monty and Cooper discretize all continuous variables and provide methods for that. But the most recent ones that I'm going to be comparing against is a copula-based algorithm that works with continuous and ordinal data. And a recent publication by Sedgwick et al. That I'm going to be describing in more detail. So there is a general way of constructing condition dependence tests. And this general way of constructing condition dependence tests requires one to have a regression model. So in the condition dependence test, we check whether this condition holds in our data, which we can write like this, or we can write like that. So X given Y and Z equals X given only Z. So essentially, you don't need Y, but you can also write it in the symmetrical form like this. It's equivalent. It's equivalent if you have access to the probability distribution. In practice, you need to fit models, let's say for this distribution and this distribution, and then check if there's a difference in the likelihood of the data with these models. In fact, Fisher has proved that you can fit two models and compute the statistic, this statistic, which is the difference between the log likelihood of the models doubled. And this statistic is distributed as a chi-squared distribution with some degrees of freedom that can be computed like this, from which you get the p-value. Now, the problem is you could fit a model for X here and a model for X here and use this formula and produce a p-value, or fit a model for Y given X and Z and Y given Z and produce a p-value. So you could produce two p-values for the same independence. Depending on the type of variable that you have, you could actually use different types of tests. So are both tests equivalent? They should be equivalent, right? You should get essentially the same answer. But in reality, you have an asymmetry problem, and it is not guaranteed that two tests that test exactly the same independence are going to return the same p-value. The first approach is to lift the carpet and ignore the problem and just perform any test that you want arbitrarily. The second approach is somehow to choose in a more intelligent way which test to perform. And what is suggested recently is to perform the test that is the fastest for each case, for each direction. The third approach would be to actually perform both tests and find an intelligent way to combine the p-values into one p-value. There has been work in statistics about how you combine p-values when they're independent. But this time, the p-values are actually dependent, and it has to be taken into account. So for the third approach, we can either take the minimum of the two p-values or the maximum. But there's been a relatively recent proposal in statistics how to combine two dependent p-values using this formula, which is the minimum of 2 times the minimum and the maximum. And this is what we actually propose as our method and we have simulated results. All right. So in simulation results, we try to figure out which out of the methods, if there's a problem, first of all, stemming from asymmetry, and secondly, if there is, like, which one of the methods works best. Especially in these examples and experiments, we have worked with continuous, binary, nominal, and ordinal variables. So for continuous, we build linear models. For binary, we build binary logistic or multinomial logistic or generalized ordinal logistic models for the last type. And for all combinations, we check the p-values of conditional and unconditional dependence also when we're given or condition on one variable. So here are some experimental results. And essentially, the lines here depend on the two types of asymmetrical tests that one needs to check. And the y-axis is how many times the performing a regression on X or performing regression on Y gives you the same p-values. And you see that essentially asymptotically, here, I mean, the y-axis is not in the same range, but asymptotically, if you check, all the decisions, the asymmetry problem goes away. You're going to be making the same decisions based on the p-values, no matter which way you perform the test. But for relatively small sample sizes, okay, there is a discrepancy. So you get different p-values if you actually do it one way or the other. So we also check the type 1 error. That means the false positive error. And if you use a threshold of 0.05 for making decisions based on p-values, you should get a type 1 error that is equal to the threshold, to 0.05. So ideally, the method should be right on the black line, every method. And here is, when you have linear and binary, the p-value that you get from regressing on the linear variable, the p-value that you get when you're regressing on the binary variable, or when you regress on both and you take in the mix the mean p-value, the max p-value, or the combination using the formula I showed you that we use MM for mean max, right? What was it? Well, this one, mean. Okay. Actually, mean of whatever. MM, it's called. Okay. So ideally, we would like the test to be calibrated and be close to the threshold. And essentially, most of the times, I mean, for various sample sizes, the lines are close to the threshold. But there are cases like this one, when you have a variable that is multinomial and the other variable is ordinal, that the only test that is actually in this range is the MM test. And the rest are not calibrated. So if you're computing only one way or the other way, or you're taking the mean or the max, is not sufficient. So these are simulated results for one test. Then we experimented with simulated data for whole networks and compared against the networks that we find when we use the test employed by this and introduced in this paper, or with Sedgwick, that we call fast because it performs only one test, the test that is going to be the fastest. And actually, the fastest test is going to be when you do linear regression, then logistic regression on a binary outcome, multinomial logistic, or ordinal regression. So this is the priority of tests to perform if you have when you have a choice. Okay, so when we check the precision of the orientation of the edges and compare them, compare the outcome, the reconstruction of the algorithms with the true graph from which we simulated the data, we see that most of the time the method is the best and gives you the higher precision, whether you have sparser networks or denser networks. For small sample sizes, this method looks a little bit better in terms of precision. When we check the recall of the orientations, the situation is reversed. So we cannot really say that this method dominates. Okay, and it's also weird that as you increase sample size, this is actually, it becomes a little better. Okay, so this is the precision and recall of the orientations of the edges, but we have introduced in 2006 another measure of performance of reconstruction of the graphs called structural Hamming distance, which takes into consideration both all sorts of errors. And it measures how many corrections you need to go from the reconstructed network to the true network, without going to more detail. So the lower the structural Hamming distance, the more your network that you found from the data resembles the true network. And basically, so when you count everything in, not just the orientation of the edges, the method actually works the best and has the lowest reconstruction error. And it's most of the cases, if you do a statistical significance test, the difference is significant at the standard level of 5%. And I would actually say that the difference also increases with a copula at least. It increases with increasing sample size. Some limitations of the method is that performing both tests is not always easy for all data types. And particularly if you try to, say, regress a continuous value, continuous variable, with using as a predictor a censored variable, let's say a time to event variable in survival analysis. I mean, this is difficult. I haven't seen any statistical method doing that. But you can still handle this by performing only one test and not doing the symmetrical correction. The tests also assume correct model specification. So if you perform a regression, like let's say linear regression, and your functional relationship is not linear, then you may have a problem with the p-values that you actually get. And there's another limitation that even if the network is correctly specified locally, because you check, you condition on variables that are maybe far apart in the network, you may miss dependencies. I would really like to thank the anonymous reviewer for this. I don't know if it's in the room, but let me give you an example. So imagine you have this network here, and this is a nominal variable, takes 3 values, and the distribution of x depends on the values of y. The distribution of z is continuous and depends on the values of z, all right? And this is the distribution of x and z. So in this case, you would expect that x and z are dependent, but actually, if you perform a test on this data, it will give you independence. So essentially, because of the way you perform the tests, you are missing some dependencies because you're working on the marginal of this network, just x and z. So even though the network is correctly specified for all subparts and all locally, the tests are not going to be correctly specified. And so this is a really good, open problem to work to solve when you're working with causal discovery for mixed data. Okay. So 99% of the papers with Bayesian networks either use all continuous variables or all discrete variables. But actually, when you try to apply this in practice, guess what? I mean, not all the data in the world are all continuous or all discrete. Okay, so this work here and Sedgwick's work and other ones, I think there's another talk today, are trying to extend these technologies so that we can learn graphical models or perform feature selection from mixed types of data, and I think that's quite important in practice. The tests that I presented today are essentially for nominal, ordinal, continuous, and so forth, but essentially the results should extend to many different types of data, such as long as an appropriate regression model is available. The main result that we find is that it is important and reduces your reconstruction error if you perform both tests in each direction, and then you combine the dependent p-values with a statistically based formula. Now, what I didn't mention is that when you use only one of the two tests, the fastest one, usually it's 7-8 times faster. Okay, so of course performing both tests increases the computational time, but actually I think it's worth the trouble. Okay. Well, that's my talk. I think this time I was in time.